Okay, hi multi. Here we go. So I believe we did question number 1 in class. However, I did say you can skip part D. It does require a reparametrization. But as Tommy said, you could also do just adding unit vectors from this point. Okay. But I don't know. I mean, I already told you you can skip it, so go ahead and skip it. For part C, you do have to find the cross product of 410 and 1263. These are the two vectors that are parallel to line 1 and line 2, respectively. So when you cross those two, you'll get a vector that is perpendicular to both L1 and L2. Okay? I believe we did all this in class, so I'm just going to let you take a look at it here and pause if you need to. Question number 2 we also did in class, I think mostly. Yeah, we got to this point. So del F is constant, which makes sense because the surface is a plane, and if you're on a plane or a quote-unquote flat surface, the direction of increase is going to be constant no matter where you are on the plane. If your line is falling on this plane, there are two things that have to happen. The first thing I did here was I said, well, that means these x, y, and z subbed into x, y, and z of the plane should make the equation true. And already I kind of look at that and I just already abandoned ship and said, I'll come back if I need to, but that just seems more work than I need to. And this is kind of the aha moment I shared with you in class. The aha moment is that if this line is on this plane, then the dot product of the vector parallel to the line and the vector perpendicular to the plane, that dot product should equal 0, which means m equals -10. And then you have a couple of ways you can go from here, and the most direct way is to just rewrite your parametric equations of the line. Notice here I did sub the m back in. And if this line falls on the plane, it has to fall on the plane for all values of t. So I just subbed in t equals 0, and I got this point, k, 1, 4. And if k, 1, 4 has to fall on the plane, then of course k has to equal that. Okay? Part C is a great question. You have to actually find the distance between this point and the plane, because that distance will be a perpendicular segment, so to speak. That distance segment will be perpendicular to the plane, and then that'll give you the length of the sphere's radius. So I ran out of room here, but here's a drawing. So here is any point that falls on the plane. I picked the easiest point I could think of. And then here is the vector n. This is the vector perpendicular to the plane. Here is the point that's not on the plane. I created this vector right here from the point 0, 0, 2, and that gives me this vector here. And the distance, d, is none other than the magnitude of the projection of this vector onto the vector n, which is right here. And you may have had to go look up how do you find the magnitude of a projection, but it's none other than dotting the two vectors, dividing by the magnitude of the vector you're projecting on, which is right there. You'll notice here I did not even bother to clean up my final expression. But this is r, and so this is, look at my gross r squared, and here's my center, the equation of the sphere. Okay? Question number 3. First of all, here is the region. Here are my two double integrals. Pretty straightforward. Notice I did not do this, because I'm going to just say I don't need to. Number 4, nice little review of contour plots. I had the advantage of color coding, so here are my different contours here. Okay. Notice that the gradient is longer, which makes sense if you think about it, right? So if you look at kind of the way these parabolic contours are oriented, the distance that one has to travel is going to be farther at this point to get to the next higher elevation than here, so hence this gradient being longer at these points respectively. Part C, parametric equations of the line tangent to, so here's that purple line. That slope is -1/4. -1/4 is perpendicular to the slope of this vector. And there's a couple of ways you can go about parameterizing a line in 2 space. Many of us probably just did this. Okay. Here, then set x equals to t, and then there you go. Okay. Straight up chain rule question. Really like this one. Interesting tree pattern, right? Z is a direct and only function of U, but U is a function of X and Y. So here is me just first finding all the pertinent partial derivatives, and then this is this. I subbed in the requisite partial derivatives that I know. These two terms do in fact cancel, so I do get 0. Therefore, I have proven that up here. I didn't do it for this example because I think you know how to do that. I mean, one thing that I'll show you here is just did not mess these things up, right? Like the partial derivatives of here. So du by dx, for example, is going to equal e to the xy times y, okay? Okay, and we did this optimization in class today. I'll leave it here if anyone wants to look at it further. I believe we did this optimization. Oh yes, right, this was the Yam's way, and then we called this Reese's way, and it worked out either way, and I think I agree Reese's is a bit cleaner. And then here is the widget, the gizmo. This was really fun to go through. So a couple of things here. Be careful with all your partial derivatives, but here is my del f, or my del t, and here's my del g, and then here is my system. And just watch all those really tricky decimals, but this question works out really beautiful in the end. Now, when I looked at this, I don't know what you thought, but the first thing I thought to myself was, let's just set lambda equal to each other. And when lambda equals everything, I get this. And then I created two different equations. So I equated these two, and I get this. And take a look at this algebra. It's so great. I equated these two. I get this, which simplifies to this, which simplifies to this, which simplifies to this. Isn't that lovely? And then I equated these two, which simplifies to, ignore the 2 for right now. Well, no, you can keep it, but the original was just the green here. This is me now simplifying, and when I simplify, I get all the way down. I get r equals p. And then what I did was I just subbed p, f, and r into the constraint equation here. So here's 200f plus 80p plus 40r equals 4,000. This will allow you to solve for p, which will then allow you to solve for r and to get f. And that, my friends, is it.